In 1980, the Austrian military asked for a new service pistol. Every legendary arms manufacturer in Europe wanted the contract. Heckler Koch responded, SIG Sauer responded, Beretta responded, Herstal responded, Steyr Mannlicher responded. Together, they had centuries of firearms experience. Then a 52-year-old manufacturer from a small town outside Vienna read the same specifications. He had never designed a gun. His company made curtain rods, window fittings, and plastic knife handles. 3 months later, he had a working prototype. It had 34 parts. It used a polymer frame when the industry still trusted steel and aluminum. The Austrian military tested it in ice, sand, mud, salt water, and thousands of rounds of fire. It kept working. This is the forensic engineering breakdown of how an outsider with zero gun design experience built the most disruptive handgun of the modern era. By 1980, European firearms manufacturing was defined by centuries of metallurgical heritage. Industry leaders like Beretta, SIG Sauer, Herstal, Heckler Koch, and Steyr Mannlicher operated under a shared, unquestioned design philosophy. Handguns were built from heavy steel forgings and aluminum alloys, relying on exposed hammers, manual safety levers, and decockers. These complicated mechanisms required precision milling, extensive machining, and skilled bench craftsmen to hand-fit dozens of small internal components. A standard military sidearm of this era typically exceeded 70 separate parts. Because these designs had performed reliably in multiple conflicts, the old world establishment treated mechanical density as a mark of quality. The dominant manufacturers assumed that safety and reliability required physical switches, external controls, and substantial metal frames. This orthodox approach made handguns expensive to produce, heavy to carry, and highly labor-intensive to maintain. It was a mature, intellectually rigid industry where progress was measured in micro-adjustments to existing machinery, leaving legacy producers unprepared for an outsider who viewed a handgun strictly as a modern manufacturing problem. In early 1980, the Austrian Ministry of Defense issued a formal tender designated the P80. The military sought a modern service sidearm to replace its aging Walther P38 pistols. This procurement process bypassed traditional brand prestige, establishing a cold, highly systematic engineering evaluation. The official scoring rubric allocated 40% of the weight to durability, 30% to reliability, 15% to weight, and 15% to cost. To qualify, any submitted prototype had to chamber a high-capacity magazine of at least 15 rounds, operate without manual external safety levers, and maintain a consistent trigger pull for every single shot. Most demanding were the environmental trials. A successful design had to survive sub-zero freezing, sand, mud, and saltwater immersion, while firing a minimum of 15,000 rounds without a stoppage. The military also demanded 3 distinct internal safety systems to prevent accidental discharges during sudden drops. For Europe's elite firearms manufacturers, long accustomed to dominant market positions, the P80 contract represented immense commercial prestige, millions in state funding, and a coveted military validation. The Austrian military structured the competition as a rigorous test of modern manufacturing limits. In 1963, Gaston Glock founded a small manufacturing business in Deutsch Wagram, a quiet town near Vienna. Glock had no background in firearms design. Instead, his workshop operated a second-hand metal press to produce curtain rods, window fittings, and doorknobs. Over the next 2 decades, the company expanded into military knives, polymer-handled entrenching tools, and machine gun belt links. This work was defined by the rigid realities of high-volume manufacturing, tooling wear, polymer chemistry, and dimensional tolerances rather than traditional weapons lore. Glock's operation relied on modern injection molding and systematic quality control. He approached manufacturing with a strict engineering principle. Every single part had to justify its existence. While traditional European gun makers focused on hand-fitting metal components, this Austrian workshop specialized in repeatable, highly automated production. When the Austrian military announced its search for a new sidearm, Glock bypassed the assumptions of the firearms industry. He approached the pistol strictly as a manufacturing and design problem, confident that his expertise in polymers and precise steel stampings could produce a simpler, more reliable tool. Glock began by purchasing leading handguns of the era and consulting military ballistics experts to understand the core mechanics of firearm design. Yet, he did not treat their expertise as law. Instead, he used their insights to systematically interrogate the mechanical status quo. Where veteran armorers saw indispensable tradition, Glock saw redundant components and unnecessary manufacturing friction. He questioned why a modern sidearm required complex external safety switches that increased both production costs and user steps during a crisis. He analyzed the frame, calculating how many parts could be eliminated if the traditional external hammer was replaced with a simplified striker-fired mechanism. Every component was scrutinized under a single, unyielding engineering rule. Every part had to justify its existence. By substituting heavy machined steel with injection-molded polymers, he sought to reduce weight while combining multiple functions into a single molded component. It was a process of subtractive engineering. Industry observers would later note that this pure problem-solving posture allowed Glock to bypass historical craft, treating the handgun strictly as a manufacturing puzzle requiring radical simplification. The first physical proof of this subtractive philosophy was a mechanism of radical scarcity. While a standard military sidearm of the era required more than 70 separate components, Glock's design achieved full functionality with only 34. This represented a rigorous application of systems engineering, stripping away excess to reveal utility. In this minimalist architecture, every component was forced to serve multiple roles. A single spring did the work of 3. The polymer frame itself served as both the structural grip and the housing for the entire firing mechanism. At a systems level, this reduction transformed the economics of production. Fewer parts meant fewer individual elements to machine, fewer tolerances to align, and fewer components to assemble on the factory line. But the true genius lay in reliability. In any mechanical system, every interface between two parts is a potential failure point. By cutting the component count in half, Glock mathematically reduced the risk of mechanical breakdown. Simplicity became the advantage, driven entirely by strict engineering discipline. Glock's decision to build the pistol frame from polymer was a deliberate production decision rather than a stylistic flourish. Synthetics were not entirely new to gun making, but the establishment still treated polymer with active suspicion. Glock recognized the material's immense manufacturing advantages. Injection molding allowed frames to be produced in seconds, with consistent dimensional tolerances, bypassing the costly milling required for traditional metal receivers. The material itself, a proprietary, glass-filled nylon branded as Polymer 2, possessed a tensile strength that rivaled aluminum alloys while reducing overall weapon weight. It absorbed recoil and offered complete corrosion resistance. Yet Glock did not rely on synthetics alone to manage the violent forces of discharge. The original patent drawings reveal a hybrid design. Small steel rail inserts were stamped and embedded directly into the frame during the molding process. These reinforced metal components handled the physical friction and stress where metal was structurally necessary, while the surrounding polymer served as a lightweight, protective shell. By treating polymer as an industrial asset rather than a novelty, the design matched the realities of modern mass production. While reducing parts lowered production costs, it also transformed the human interface. Traditional military sidearms of the 1980s were crowded with manual thumb safeties, external hammers, and decocking levers. In high-stress situations, these components demanded split-second cognitive decisions from the operator. Glock removed these external controls. By eliminating manual switches, the design established a single, uniform action. There were no safety levers to disengage. Operators had no external hammers to cock. This layout reduced the physical steps required to operate the weapon, turning it into a direct tool of utility. By minimizing the physical interface, the design reduced human decision-making under pressure. Simplicity became the operating advantage. Historically, firearms safety was defined by redundant physical barriers, heavy metal switches that locked the trigger, blocked the hammer, or disconnected the firing mechanism. Traditional gunsmiths treated safety as an active checklist of manual procedures. Glock challenged this convention by integrating safety directly into the cycle of operation. Instead of a manual thumb lever, the design incorporated 3 independent automatic safeties within the internal architecture. There were no external switches to flip and no levers to search for under duress. The pistol remained safe until the trigger was deliberately pulled, returning to a safe state the instant the trigger was released. By automating these safeguards, Glock questioned whether a firearm needed to conform to familiar appearances to protect the user. This departure simplified the mechanical layout while altering decades of training protocol. It forced military evaluators to reconsider their relationship with their equipment, demonstrating that safety could be a function of mechanical engineering rather than historical habit. In May 1982, the Austrian Ministry of Defense subjected the prototype to a series of physical trials designed to force mechanical systems to complete failure. Under the official P80 procurement guidelines, a candidate sidearm had to survive conditions that typically seize traditional handguns. Military evaluation records document the exact parameters of these endurance runs. The prototypes were baked in high-temperature ovens, above 100 degrees Celsius, frozen solid in blocks of ice at minus 40 degrees, buried in abrasive sand and choked with thick mud. They were submerged in salt water for 24 hours to test the limits of chemical corrosion. Throughout these trials, the polymer reinforced frame and its 34 parts remained structurally and mechanically intact. While competing designs from legacy European manufacturers suffered stoppages, with at least one rival failing the mud fouling test entirely, the Glock prototype fired 15,000 consecutive rounds without a single mechanical malfunction. It maintained complete cycling reliability and a consistent trigger pull weight throughout the trial. The empirical data from these trials offered clear evidence. Glock's minimalist architecture outperformed the complex, hammer-driven steel handguns of the old world establishment. By meeting every environmental and endurance parameter, this unconventional design won the contract for 25,000 pistols, officially entering military service as the Pistole 80. Europe's legacy gunmakers did not lose the contract due to incompetence. These firms were highly capable, but they operated within the constraints of their own success. Decades of heavy tooling, established product lines, and ingrained institutional habits kept them bound to traditional metal machining and hammer-fired systems. Glock possessed a singular advantage. He lacked emotional attachment to the heritage of gunmaking. While others sought to refine existing designs, the outsider saw what insiders ignored because he questioned every assumption. For Glock, simplicity became the advantage, guided entirely by manufacturing logic, free from tradition. Winning the contract was only the first step. The true challenge lay in producing 25,000 pistols. Glock's experience in high-volume injection molding allowed the Deutsche Wagram facility to scale production rapidly. The factory used modular steel molds and automated dimensional inspections, keeping frame tolerances within 0.02 of a millimeter. This disciplined approach came from years of producing curtain rods and knives, where tooling wear and strict quality control dictated profit margins. Because the design required only 34 parts, workers assembled each weapon in minutes without hand-fitting complex metal components. The process relied on repeatable automated output, reducing production costs by 30% compared to steel frame competitors. Glock understood that a successful sidearm had to be a simple industrial tool. This was manufacturing logic, not tradition. By the mid-1980s, American law enforcement faced an operational crisis. Most municipal departments still issued six-shot revolvers, but officers increasingly encountered criminals armed with high-capacity semi-automatic handguns. This disparity forced police administrators to search for a new standard sidearm. They needed a weapon with higher capacity and absolute reliability, but it also had to be easy to transition to for thousands of officers accustomed to the simple point-and-shoot mechanics of a revolver. Glock arrived in the United States at this exact moment of institutional transition. The Austrian pistol offered a 17-round capacity, a lightweight frame, and a consistent trigger pull with no manual safeties to train around. For major departments looking to standardize training and reduce maintenance budgets, Glock was not a novelty. It was an efficient organizational solution. Despite immediate technical success, the pistol faced stubborn cultural resistance in the United States. Critics labeled the polymer frame as cheap, dismissing the lightweight design as unsafe and untraditional. The lack of manual external safeties and the boxy, unfamiliar profile drew intense skepticism from veteran officers. But physical proof slowly eroded these doubts. As police departments subjected the weapon to rigorous evaluations, the simplicity of the design proved its real-world utility. Simplicity became the advantage. Over the next decade, this once scorned outsider systematically replaced traditional revolvers, transitioning from a mechanical anomaly into the global standard for modern sidearms. The firearms establishment had centuries of experience. It took a curtain rod maker to remind them what engineering is supposed to do. Subscribe for deeper dives into the engineering stories that reshape our world. In the decades following the P80 trials, the global firearms market underwent a permanent structural realignment. According to Paul M. Barrett's documented history of the company, the radical features once ridiculed by traditionalists gradually became the industry standard. Polymer frames became normal, striker-fired designs became dominant, and simplified controls became mainstream. Competitors who once dismissed Glock's synthetic frame eventually adopted major elements of his design philosophy. This shift reveals a broader principle of industrial design. Established experts often spend generations optimizing within inherited rules, while outsiders succeed by questioning the rules themselves. Glock bypassed traditional gun-making heritage entirely, succeeding instead through strict manufacturing discipline and first principles engineering. The firearms establishment had centuries of experience. It took a curtain rod maker to remind them what engineering is supposed to do. Subscribe for deeper dives into the engineering stories that reshape our world. Today, first principles design continues to disrupt industries where tradition resists progress. When complexity is mistaken for sophistication, radical simplification remains the ultimate competitive advantage. The firearms establishment had centuries of experience. It took a curtain rod maker to remind them what engineering is supposed to do. Subscribe for more deep dives into the history of engineering.